And what might be an odd introduction into our Diels Alder, what we want to do is think back to our electrophilic addition reactions, in which case we took a pi bond, or a nucleophile, or which would act as a nucleophile, and reacted that with a Lewis acid, which then potentially had a leaving group and some other chemistry going on, which acted as our electrophile. In one of the subsequent steps, you'll also notice that not only did that electrophile, or well, let's even ignore that, let's take it a step further. If we move on further down the line, you notice that we have another nucleophile that comes in and reacts with the now electrophilic carbon of our original alkene. So when we're running this kind of reaction, we need a reagent that can react as both an electron acceptor and donor. We had a variety of reagents when we looked at our electrophilic addition reactions that typically generated ring transition states. As an interesting feature for our Diels Alder, an alkene satisfies this same requirement. If we take a look at the alkene resonance structure, at one end of it we have a good Lewis acid in the case of missing electrons, and at the other end we have a good Lewis base because it can donate electrons. We've got our Lewis base, or our nucleophile, and we have the electrophile in our Lewis acid. So theoretically we could have an alkene react with an alkene. So we could take 2-butene and react it with itself to make this kind of cyclic structure. And yes, we may be looking at this and saying, well, there's ring strain and all that other fun stuff, but theoretically, if we provided enough energy, we could potentially pull this off. And that's kind of the origins of our Diels Alder reaction. But before we kind of skip into that, what we want to do is take a brief moment and think back to our molecular orbital theory. Okay, our molecular orbitals are made from the atomic orbitals. And all our orbitals have potential phases within them, shaded or unshaded, depending on what we're looking at, or which orbitals we're looking at. When we look at a sphere, we only recognize one phase, so it's always the same color shading. If we look instead at the p orbital with that 2-lobe aspect, one of those lobes is typically shaded, and this is to show a phase difference, because as we move through the origin of this drawing, we change phase. Think of it much like a sine wave. Okay? The peak here is at +1, whereas the valley at the other location is a -1. Okay, so we're seeing a transition through our origin. Okay, so when we look at the orbitals for p, or look at the drawing for our p orbitals, what we're trying to represent is that phase orientation. And so when we look at our molecular orbital theory, at its simplest level, we're just bringing our two orbitals, or hundreds of orbitals, near each other, and we're seeing what ways could they possibly interact. So in the example shown, we're taking two s orbitals, which hopefully you would realize are s orbitals because we've got that nice spherical shape, okay? And we're bringing them near each other to see how they could interact. Remember, we could have the system where they are both shaded or unshaded. Okay, so both of those populations exist for our orbital, if you will. Okay, so we have a possibility that we match shaded to shaded, or for that matter, unshaded to unshaded. Both of those interactions are going to be a favorable interaction. So we are now overlapping and allowing the electrons to jump back and forth. The result of that overlap is what's shown down below. Okay? And so our red and blue dots are supposed to represent our nuclei. So you'll notice that in this system, most of that electron density is located between the atoms. Well, if we dump a bunch of electrons between atoms, what have we formed? Well, a bond. Okay? Nice and straightforward. Where this theory becomes a little bit more challenging is that we also have to acknowledge another possibility. I could have just as easily taken that shaded and interacted it with the unshaded, or the unshaded and interacted it with the shaded. In those cases, what happens? Well, they try to overlap, but now the waves misalign. So in our bonding situation, we have one sign versus another sign where there's our origin. So when we add those signals together, they constructively interfere and we get a larger signal. But what happens if the phases are out of alignment? Okay, let's just say we had that system, and then in the next one, we had this system. Well, now when we add it up, what happens? Okay, we would lose all signal. Everything disappears. Okay, which goes to say that wherever that overlap occurred, there are no electrons. Well, that overlap is going to occur between the atoms, and if we look at the representation that we've got drawn, you'll notice there's a big empty white space. That's because there's no electrons there. And instead, the electrons start to shuttle towards the outside of the nuclei. Okay, because we don't have electrons in between the atoms, we can't refer to this to a bond. In fact, it's the opposite of a bond. It is the lack thereof. But this pattern is still possible, or orientation is still possible. So we'll refer to this as the anti-bond. Okay? So when we're asking for molecular orbitals, that's really all that's happening. We're taking two orbitals, we have them interact, we see what happens. If we move to larger and more complex structures, we may be taking multiple orbitals and seeing how those multiple orbitals interact. But ultimately, in all cases, we're taking orbitals, atomic orbitals, and we say what happens when they interact. Okay? So let's push this a little bit further. What's useful about this? Well, if I said this was a hydrogen atom, well, hydrogen comes in with one 1s electron. Okay, if I have two hydrogens that have one 1s electron, I can have them interact with each other. That's going to generate these new potential orbitals. Okay, not even potential, these orbitals now exist. Deciding whether or not we have a molecule, i.e. the orbitals are filled appropriately, then depends on where we place the electrons. So we will take the electrons from our atoms, and we need to fill them into the molecular orbitals, which are now through the middle. So we'll total our atomic electrons, this case 2, and we will place those electrons into our molecular orbitals. Okay? In this case, we want to put them, or in all cases, we want to put them as low energy as possible, so we would populate that lowest orbital with our 2 electrons. We can then go and evaluate the balance of our molecular orbitals. Are we primarily bonding occupied or non-bonding or anti-bonding occupied? Well, in the case of hydrogen, we're bonding. Most of our electrons are located in the bonding system. Okay? If we scale this up to, say, helium, okay, well, helium now is still using 1s electrons, but there's now 2 of them. So what we would have to do is take those 4 now electrons and dump them into our molecular orbital system. Well, what happens when we move them into the molecular orbital? We'd fill 2 in the bonding, but we'd also fill 2 in the non-bonding. So now we have this kind of cancellation occurring. And you'll notice that the way I've got this drawn, the non-bonding is higher in energy than the bonding. Okay? This ends up meaning that the overall weight for the bonding description of our molecular orbital is that we are primarily anti-bonding, which means we don't get a bond or don't predict a bond between 2 helium atoms. And sure enough, if we go back to think to our diatomic atoms, helium is not one of them. So this does give us some kind of useful predictive power. The other thing that you may end up seeing would be p orbitals, and p orbitals do much the same thing. Okay? In the drawing that I've got shown over here, I've taken it a step further, and instead of looking at p orbitals, if we look at those shapes, those aren't quite perfect. Those are actually hybrid orbitals, some combination of s and p. Okay? But it's really just the same. I'm now going to take those 2 orbitals, and I'm going to bring them near each other to see how they interact. Well, there is a potential for the largest portion of their electron density to overlap with the same phase right through the middle, which then means I have a bond. Okay? Likewise, I could have overlapped them in such a way where I don't get the electron density there, and I end up with the anti-bond. So when we go through and look at reactions, we're really trying to say, okay, what's changing? What orbitals am I using to make new bonds? What orbitals are breaking, okay, or shifting to account for these kind of changes. So if we take this now theory and apply it to our diene, or our two double bonds, to see how this reacts, we need to go through and decide, well, what things changed. If we evaluate critically, we're starting sp2 in each of those cases, and we become sp3 in our products. So really what's changed is I've lost a p orbital. So in the reaction of these two starting materials, I'm really concerned about how the p orbital becomes, or a non-hybridized p orbital becomes a sigma bond. Okay? So that means when I look at my molecular orbital diagram, I want to keep my focus on the p orbitals, okay? Because those are the ones involved in the double bond of my starting materials. Okay? And then likewise I would jump it out to the product. I was kind of hoping that that product didn't show up, but oh well. So let's just pretend that's not there. So if we go through and look at each of those, we have the potential where our p orbitals align, and we have the potential where our p orbitals do not align. So we have a bonding system and an anti-bonding system. Well, the other double bond is going to do the same thing. Okay? And if we try to populate these with the electrons, remember we're taking the p electrons in this case, so one from each carbon. When I'm starting with my 2 pi, or 2 p orbitals, I end up with 2 electrons. So my 2 electrons would occupy the bonding orbitals. Okay? We can then propagate this out further into what's happening with our final product. Well, in the case of our final product, we are forming a new sigma bond, in fact 2 new sigma bonds, okay, by having that electron density overlap appropriately. So we're converting the p orbital into a hybrid sp3 orbital to form that bond. Okay? Or we would form the anti-bonds, okay, where they don't overlap. So we're kind of following through a balance of this. You might say, well, then why don't we just form our bonds? Okay, well, we have to look at this and evaluate, is this a possibility? How is this going to come together? To get these orbitals to overlap, you'll notice that they have to be shaded the same in both cases. That means when we take our reactants, we have to make sure that I get that reactant, or those orbitals, overlapping exactly with those orbitals to form the bond. Okay? So that the shadings match with what we would expect in the product. Okay? What you might then notice here is that we have a dilemma. What we are trying to do is take these 2 electrons and these 2 electrons, and we are trying to dump them into the exact same orbital. Okay? Well, an orbital can only hold 2 electrons, so that interaction is not allowed. Can't happen. Okay? So that setup doesn't work. There's no space to put those electrons, so I cannot combine those 2. Okay, well, we have another orbital. Okay, we do have the anti-bonding orbital up here. So instead of trying to combine the electrons from my 1 double bond into the place where there's already electrons, I'm going to try and slide them into the empty orbital. And this could potentially set me up with a bond. However, what's the issue? Hopefully what you see is that our shadings do not match. And I deleted everything. That's always fun. Well, hopefully what you saw was that the shading didn't match. Okay, what does that mean? Well, that means those orbitals cannot, or we can't run the electrons from our leftmost to the rightmost. Okay? That means this reaction of attempting to form this new product here is not allowed. It's a bad reaction. Okay? And because of how we go through and phrase and label these, it is referred to as forbidden. Okay? Can we make it happen? Yes. But that gets a little bit trickier. I need to somehow set this up so that when these two molecules react with each other, the orbitals do align appropriately. Okay? And I cannot get these two to match, and I cannot get these two to match. The matching must somehow occur up at the top. But that can only happen if there's electrons there. If there's no electrons, I can't form the bond. So how can I potentially get the electrons in this lower orbital to move up to a higher orbital? That's a challenging question. Think about it. If you come up with an answer, try and test me in class. Back to our primary point, our Diels Alder reaction. Okay? If we just went through this alkene with an alkene and said not going to happen, what would we expect now in this situation? Okay, well, this one adds an extra double bond. Okay? And it turns out that that extra double bond makes all the difference in the world. This reaction is incredibly fast and favorable. This is one of the reasons why it gets named after Diels and Alder, because they went through and did this and said, hey, this actually worked. Okay? And then we have to propagate through and figure out why. Well, we can go back through and look at molecular orbitals and look at all the pairing up of this and what we would expect to end up happening in the product. Okay? I leave it to you to go through and deal with that coloring or shading in and then matching the orbitals to see how that would align and how that would potentially work. And what you should see is we get a direct lineup without any weird bumping around of electrons. Okay? For those of you that are interested, talk to me in class and we'll go over it. So, to the Diels Alder reaction. Okay? What we want to do is look at how this reaction works and potentially come up with a mechanism or an explanation of it. So when we look at any reaction, once we know it actually runs, we need to start to focus on what changes occurred. And in this case, we broke some bonds and we formed some bonds. So we want to know what those bonds are. Okay? And here we'll have a little quiz before we continue on. But what we did is we took the pi bonds on what was called the diene, because there's two double bonds, and the pi bond on the dienophile, and we shuffled those structures around. Okay? All of those pi bonds are broken. So in our broken system, we broke 3 pi bonds. Whoops, and my color coding is a bad system here, so let's fix that. We broke 3 pi bonds. But then what did we do? Well, we made a new pi bond that wasn't there originally, and we made 2 sigma bonds. Okay, so we have 1 pi and 2 sigma. We could go through and kind of do a process here. We could say, well, then the net result is that I broke 2 pi bonds and I made 2 sigma. Okay? And the exact orientation of this is going to become important, so kind of focus on that. I would make the argument that we actually didn't break 2 pi bonds at all. That really all we did in the process of this reaction is that we made 2 sigma bonds, which is kind of a challenging concept. Okay? So what I want you to do is think about how and why it is only 2 sigma bonds that we should be concerned about. Okay? The next part of our question when looking at a mechanism is that when did these sigma bonds form? Because really we have 2 different ones. We could call it sigma 1 and sigma 2. Okay? So now the when question is really looking at our mechanism. Okay? Well, only 2 things happened here. So this should start ringing bells when 2 things happened before. Like, I don't know, a leaving group leaving, and a nucleophile forming a bond. Like our substitution reactions. So what we're looking at now is that we have 2 possible mechanistic styles for this. We can call this Diels Alder 1, make sigma bond 1, then make sigma bond 2. Or we could call this Diels Alder 2, make sigma bond 1 and sigma bond 2 at the exact same instant. This should ring bells back to our substitution reactions. Okay? And the reason we want to evaluate and look at this is that back when we looked at our substitution, notice that what did we see when we ran those individual mechanisms? Well, if we ran under SN1 conditions, we got 2 products. If we run under SN2 conditions, we get 1 product. How do we know both mechanisms were active? Well, depending on the conditions in our structure, we saw differing amounts of products. Okay? That's what our experimental results give us. So what we're going to do with our Diels Alder reaction is we're going to design our reagents, or use our reagents, to help us then decide with the end result, did we get 2 products or 1 product? If we get 2 products, that means we're likely running under the 1-type mechanism. If we get 1 product, we're likely running under the 2-type mechanism. So our experiment will hopefully allow us to see this and differentiate between these two. Okay? But before we start, we run into kind of a big repercussion of our alkenes. Okay? If we have our alkenes interact, remember, it's our p orbitals that are then interacting with each other. We are trying to get this p orbital to interact with this p orbital. We're trying to get this p orbital to interact with this p orbital. Okay? Well, p orbitals have lobes. We could have that interaction occur from above the diene or below the diene. Okay? Well, we might say, well, is that really relevant? Do we care? Okay, well, that's going to then come down to propagating our structure out and seeing what we get. Well, what is the relationship between those two structures? So a couple things to assume. That red C is marked for a reason. That can't be exchanged anywhere else. That is now permanently locked in as a red carbon. Okay, the other thing we'll assume is that we don't do any sigma bond rotation. Let's just leave it at that. What is the relationship now between those two structures? That's a trickier question, which hopefully you'll be able to answer. The biggest issue that comes out of this is your Diels Alder reaction can, and very often does, result in some type of stereoisomer. So that means if we think back to our SN1 conditions where we only ended up with 2 or 1 product, the alkene is necessarily going to force 4 or 2 products. That can mess up our answers. Okay? In our further analysis, I want to kind of keep with just one of these potential reactions, either the sigma up or the sigma down. I personally think my sigma down looks a little bit cleaner, and so that's going to be the one we're going to use to discuss the rest of these mechanisms. So let's evaluate our guess mechanism for DA1. Okay? This was our stepwise mechanism. Okay? We said to form sigma 1, then, as a second step, sigma 2. Okay? That was our primary goal. So if we go through and look at what I've got drawn, we're taking the pi electrons from our diene, we are sharing them, okay, with the carbon of our dienophile. This then causes an octet explosion, if you will, okay, or an octet fail, which then has to necessarily force the electrons out of that pi bond onto the next carbon, okay, instantly. This isn't a multi-step thing. It has to all happen as one fell swoop. Okay? The result is we would end up with a structure like this. Okay? The dashed line showing where my bonds will potentially form, the solid line showing where bonds currently are. Which can be a bit confusing, so if we clean it up without the orbitals, what we'd end up with is something along these lines. Okay? The interesting feature of this product is that I now have a sigma bond chilling right here. Well, the fun thing about sigma bonds is that they can rotate. If that sigma bond rotates, that is going to change the relationship of A to C versus B to C. Okay? So if we propagate this out and close that final loop with our second step, the negative charge attacks, our double bond shifts around, okay, and we'd end up closing our ring. Depending on if we rotated that sigma bond or not, we would end up with one of these 2 products. Remember, this is only in the sigma down conformation. We also have the sigma up to consider theoretically when going through this. Okay? So our guess mechanism 1 results in multiple products. Okay, or multiple types, ignoring the stereoisomer issue. Well, what happens in DA2? Well, in Da2, we said everything must happen at the same time, okay, or simultaneously. Well, if it's simultaneous, I need to take the electrons from my pi bond, have it from my diene, and have it react with a dienophile, which then, again, we have an octet fail, which means the electrons from that pi bond must shift out to form a new double bond, or a new single bond, sorry, by reacting with the other carbon, or the opposite carbon in the diene, which then again causes an octet fail, which then pushes the electrons further around to make our final structure. Okay? The interesting feature in this is that while we may have formed a sigma bond, great, we may say, okay, well now let's take a look at the rotation of that sigma bond. Okay, well, but that sigma bond is now locked into a ring. The ring prevents rotation. This means that when we look at our two mechanisms, the Da2 produces quote-unquote one product, and our Da1 produces two products. We can use this to help us predict which mechanism, or design an experiment to decide which of these two mechanisms is valid. Okay? One of the things I want you to go through and prove is all of the drawings that I've gone through and set up here. Okay? So get a model kit out. You've got the picture in the lower right-hand corner as an example to set this up, and make sure that you can see how these different structures or these different drawings can potentially come out of these results. Okay? Because if you can't see or visualize those, this is where the model kit will help. For those of you that think you're gods at this, you're wrong. Get out the model kit, figure it out, and make sure you're comfortable with those manipulations, because you will find that the Diels Alder mechanism is massively spatially organized, and it will destroy you. Okay? So, back to our experiment. Okay, we need to choose starting materials that would allow us to see the formation of the different product in our guess mechanism 1. Okay? We don't care as much about the guess mechanism 2, because the guess mechanism 2 only produces one product. Okay? Guess mechanism 1 is the one that's going to get us two products. So we want to design our experiment in such a way that we can see the potential for two products. Okay? And you'll notice that one of the things that I've added in here is this extra C. Okay? That is there because if we ignore it, we don't really pick up a strong difference between the two products. We need that C, because that C orientation is what's going to lock down our difference. C will either see B or C will see A. Okay? So we need a structure that has a functional group or something characteristic at location C and at either location A or B. Okay? So if we propagate this backwards, let's clean that up, we need a double bond for our diene with a C on it, and then we need a difference between A and B. Okay, well, if A and B are different from each other, and C is not H, what do we have? We have a structure with cis-trans isomerism. Okay? So that needs to be a characteristic of our dienophile. Okay, so that's going to help us choose what pieces we put into this. Okay, so it has to have this cis-trans isomerism. Okay, the next big part is how do we nullify this up-down enantiomer issue? Because that is really going to throw a big monkey wrench in our whole process. Okay, so if we look at what we've got drawn here, we want to somehow prevent our dienophile from sitting up top. Something has to be up here. You know, a little sword, that's a sword, let's call that a sword, swinging away, preventing the diene from getting up there. Okay. Well, what would prevent the diene, which is made up of electrons, from interacting up there? what are electrons afraid of? Electrons are afraid of electrons. So if we take a look at this drawing, we have our diene, okay, with an extra carbon connecting it. What does that extra carbon do? Well, because we have a 5-membered ring, we have a slight pucker in the structure. That pucker puts a carbon with electrons on, it's kind of arbitrary, but in this case our sigma up direction. What does that do? Well, that should nullify our sigma up product, and we should only end up with the sigma down. Cool result. That actually sets it up where we now will end up with only 2 products or 1 product. Nice and clean. Okay. The next part of this, if you can take a second to pause here, try to draw the products out of this. And it is a tricky one to go through and draw because of the orientation of all of these structures. You're going to have to try and draw something in 2 dimensions that is 3-dimensional without wedges and dashes. It's kind of a pain in the butt. Okay, but see if you can draw both those products. And now I'm going to assume you've done it, and this is what they end up looking like. You'll notice that I added the hydrogens into the structure so that we can better see that. For those of you paying attention, the previous slide, I said that our dienophile, okay, the one with just the 1 double bond, needed to have cis-trans isomerism. Is there something problematic with the diene I drew here? And now I'm going to have to say sorry, because I've talked too long. We will reveal more about the Diels Alder reaction after you guys have completed it. Okay? For those of you that weren't in lab, I will announce when the next video is available, and I will post it to Canvas so you have access to it, where you can go through and actually see the exciting conclusion of our experiment. Thanks for listening and working on the quiz.